Hi guys, welcome back to the channel. In this lecture, we are going to discuss one problem on plastic analysis in which we need to find the required plastic moment capacity of this prop cantilever beam. Okay, so in this problem, 2-point loads are acting on this prop cantilever beam, right? One is acting at C and one is acting at D. And this problem, the load factor is given, which is equals to 2, right? So in the previous problems, we discussed about how to calculate the plastic moment capacity. Okay, how to calculate the plastic collapse load. Okay, here we need to calculate what is the required plastic moment capacity to sustain this loading system having load factor of 2. Okay, so let us discuss about the what is load factor. So load factor is equals to collapse load over my working load. Okay, as you can see that in this problem the working load are 75 and 30 kilonewton load. Okay, and load factor is given 2. So collapse load will be 2 upon my 75, 2 upon my, this is, let us suppose the collapse load is X and this is working load is 75. So X equals to 150 kilonewton. Similarly, the 30 kilonewton load will become 60 kilonewton load after multiplying the load factor. Okay, so we know the collapse loads. Okay, these 150 and 60 kilonewton are our collapse load basically. So we need to design our beam for this collapse load system. Okay, we need to find this MP value, right? So load factor is nothing but it is collapse load upon my working load, right? Generally sometimes we need to find load factor also. Okay, and in which we will, let us suppose we need to find load factor. Okay, and MP value is given, then we will simply multiply 75 by some lambda. Let us suppose load factor is equals to lambda, so 75 times lambda will be our load acting at this point. Okay, so in this problem, after using the concept of the load factor, or after multiplying the working load with the load factor, our load system will become, this will become 150, okay, and this will become 60, okay, because load factor is 2, right? Now second thing is this prop cantilever, static indeterminacy of this prop cantilever beam is basically 1, okay, and number of plastic hinges required for the collapse, number of plastic hinges required for collapse will be equals to the static indeterminacy plus 1. Static indeterminacy, two plastic hinges are required to make this structure collapse. Okay, one plastic hinge will make the structure determinate, other plastic hinge will make the structure unstable, right? So this thing is clear, right? And we need to find we need to solve this problem using the concept of static equilibrium method. Okay, where we will be using the equilibrium equation in terms of moment. Okay, so now this thing is clear. So two plastic hinges are needed basically. So next step is to form the moment equilibrium equation, right? And this is very, very important. Moment equilibrium equations. Okay, so as you can see that I can divide this beam into two parts. One part will be simply supported. Here I am considering MA as redundant. Okay, MA as redundant. Okay, so here this 150 kilonewton load is acting, right? And here 60 kilonewton load is acting. Okay, and one more system will look like this, where our beam is simply supported and the redundant force will act on this beam. And the direction, I'm assuming it is acting like this. Okay, this is our MA, right? Now, if you draw the bending moment diagram, because we need to form the moment equilibrium equations, so we need bending moment diagrams. Okay, for that we need bending moment diagram. Okay, so if you need to analyze this part, this beam, and then this beam. Okay, so if you find this is A, this is C, this is D, and this is B, right? So if you find the RB reaction, RB will be RB into 6 equals to 150 into 2 plus 60 into 4. Okay, I am taking moment equilibrium about A point. Summation MA is equals to 0. Okay, so if you solve this thing, so it will be 150 into 2 plus 60 into 4 divided by 6. So RB comes out to be 90 kilonewton, direction upward, right? And RA will be 150 plus 60 minus 90. RA will be 120 kilonewton. Okay. Why we are finding this reaction? Because we need to calculate the bending moment diagram. Okay. We need to draw the bending moment diagram. And RB equals to 90 kilonewton, right? So if you draw the bending moment diagram, it will look like this. Okay. And these value we can find easily. So this value will be 120 into 2. So this value is 240. Okay. And similarly, this value will be 90 into 2 will be 180. Okay. And this is the straight line. Right? So what we did over here is we draw the bending moment diagram for this simply supported beam. Okay, now let us draw the bending moment diagram for this case. So at this end, the bending moment will be 0, and at this end, the bending moment is hogging, so it will be negative. So our bending moment diagram will look like this. So this is nothing but this is MA. Okay. So now let us find where the plastic hinges will form. At those points, we will be writing the equilibrium equations. Okay. So I can see that we need to have two plastic hinges. Okay. So one plastic hinge will definitely form at this point, this A point. Okay, because moment will be maximum over here, right? Okay. And the second plastic hinge will either form at this point or under this point load or this point load. Okay. So let us assume our first case, our plastic hinge is forming at this A and C. Okay. So let us assume plastic hinges will form at A and C. Okay. So I am writing the equilibrium equation for A and C point, right? See it carefully. So at A, the moment is positive. Okay. This will be 240 minus. At this point, the moment will be this. We can calculate using linear interpolation. MA over my 6 equals to X over my 4. So this will be 2 MA over my 3, which is equals to X. Right? So I can write 2 by 3 MA equals to MC. Okay. So first I am writing the moment equilibrium equation for this point C. Okay. So if I assume my plastic hinges are formed at A and C point, okay, that for forming the plastic hinge at A, it will result in the collapse because we require two plastic hinges. Okay. So I can write 240 minus 2 by 3 MA. This will be MA will be equals to MP because plastic hinge will form at this A point and this C point, and this is equals to MP. MC will be equals to MP. Okay. So if the plastic hinge will form at this point and this C point, it will deflect like this. Okay. So direction of the moment will be MP over here, and the MP will act like this, opposite to this rotation. Okay, so this is the case. So that's why we are taking MC equals to MP positive. Okay, because hogging moment we are considering negative, right? This 2/3 MP is negative and this MP will be positive because it is sagging, right? So if you calculate this thing, so it will be 240 equals to, this will be 5/3 of MP. Okay, so if you solve this thing, it will be, MP comes out to be 144 kilonewton meter. Okay, so required plastic moment capacity for this beam when plastic hinges are formed at A and C is 144 kilonewton meter. Okay, so we have checked the first, we have calculated the plastic moment capacity when the plastic hinges are formed at A and C. Now we will see that, now we will check the condition when the plastic hinges will be forming at A or D. Okay, at A and D, right? So now equilibrium equation for the D point, equilibrium equation for this D point, it will be 180 minus of, this will be, again we can calculate using linear interpolation, this value will be MA over MA 6 equals to X over MA 2. So this value will be MA by 3. Okay, so this value is MA by 3. So this will be 180 minus MA by 3 equals to MD, right? So for the collapse, the plastic hinge will form at A and D. Okay, at A and D. So when the plastic hinges are formed at A and D, moment at A will be MP. This will become MP. So this will be MP by 3, right? So I can replace this MA by MP and this MD will be equals to MP because plastic hinges are formed at A and D. So again, if you solve this problem, this equation, this will be 4/3 MP. So the value comes out to be, so MP equals to 135 kilonewton meter, right? So two values we are getting. So when the plastic MP is equal, this is MP equals to 135 when plastic hinges are forming at A and D, right? So two plastic moment capacity we are getting for different collapse mechanism. Now we'll see, now this is the important part, we'll see which mechanism is true mechanism. Okay, which mechanism is true mechanism. For that we will design our beam. Okay. Okay, now the part is very, very important. Okay, so we got two moment capacity. Okay, so one is, now first case one is what? When the plastic hinges are formed at A and C. Okay, for the true mechanism, we need to satisfy three conditions. One is equilibrium, right? Second one is mechanism, and third one is yield condition. Okay, and we have discussed about these three conditions in detail in the previous lectures, right? So you can see that already we are using the concept of equilibrium. Okay, we are forming this equation using equilibrium. So equilibrium condition will always satisfied in static equilibrium method. Next is mechanism. Mechanism condition is also satisfied because two plastic hinges are required, and we are saying that the plastic hinges are forming at A and C. So mechanism condition is also satisfied, right? Now let us come to yield condition. Yield condition means M should be less than equals to MP. This thing we have to check. Okay, this thing we have to check, right? So now when the plastic case one, when the plastic hinges are formed at A and C, let us draw the free body diagram of this thing. Okay, so this is our C point this is D, this is B point. Okay. So if the plastic hinges are formed at A and B, at A and C, this will be our direction of this will be our MP. So here the direction of the MP moment will look like this. Okay. Here the direction of the moment will be like this. Okay. It will be like this, right? Similarly, one moment over here MP, one load is acting at this point, which is 150 kilonewton, and here one load is 60 kilonewton, right? One load will be there, RA. Okay, and again one more reaction at this point, this will be RB. Okay, so we'll draw the moment diagram for this case. Okay, so now let us first calculate what is the value of RA. So RA I can calculate by using the equilibrium, by considering the equilibrium of A and C part, AC part. Okay, so I can write RA into 2 equals to MP plus MP. This I can write. So RA will be 2MP by 2. So MP is what? When you are assuming that plastic hinges are formed at A and C, MP value comes out to be 144. Okay, so RA is 144 kilonewton, right? Then RB will equals to 150 plus 60 minus of 144. Okay, and the value comes out to be 66. Okay, so here RA is 144 and RB is 66 kilonewton. Okay, there should be no doubt in this, right? So we have calculated the reaction. Now we can draw the bending moment diagram. Okay, so bending moment diagram I will be drawing here. Okay, so when the plastic hinges are formed at A and C, what will be our bending moment diagram, right? So at this part you can see that the bending moment is MP. Okay, this value is MP, and this is basically hogging, so it will start from this below this axis, below this axis. Okay, so this is our you can say that this value will be 144. Okay, at C you can see that the moment is MP and it is sagging moment, so it will be positive, right? So it will goes like this. This value will be 144. Okay, and again if you come at this point, the point load, the reaction from the at the C support is 66. Okay, so at this point the moment will be 66 into 2, so that will be equals to 66 into 2 will be 132. So this value is 132 and it will join by a simple line, right? So you can see that nowhere in this beam the moment capacity is exceeding MP value. Okay, so if you want to check from this side what is the moment at this point, so I can write 66 into 2 64 minus of 60 into 2. So this will give moment at MC. So this will be 66 into 4 minus of 60 into 2. So again this value comes out to be 144. Okay, so if you check the moment from this side, it will be 144. So you can see that by looking at this diagram, this is satisfying the yield condition. M is always less than equals to MP. So yield condition is satisfied. Okay, there should be no doubt in this. Okay, why we are doing all this? Because we are getting two moments. Okay, and we need to find what will be the required design capacity for this beam. Okay, for that we should know what is our true mechanism, and true mechanisms will be is that mechanism which will satisfy these three conditions. That will be our true mechanism. Okay. So now this thing is done. Now we will discuss the case 2 where the plastic hinges are formed at A and D point. Now, okay, for the case 2, when the plastic hinges forms at A and D. Okay, when the plastic hinge is forming at A and D, this is D point, this is C. So the plastic hinge will form at A and D. So at the collapse, our deflection diagram will look like this. Okay, so the direction of the movement will be opposite to this rotation. It will be MP over here, MP over here, and MP will act at this A point. Okay, you assume the direction always opposite to this rotation. Okay, so now if you consider the equilibrium of this D part, this is A and this is D. Here this moment MP is acting, here also this moment MP, here one point load will be there 150 during at the collapse, here again the MP, and here this is RB reaction. Okay, the free body diagram will look like this, and at this D point there is there is a point load of 60 kilonewton. Okay, and there will be one reaction RA at this point, right? Now we'll see something over here. Now if you want to calculate RA reactions, you need to consider the equilibrium of AD part. Okay, so taking equilibrium of AD part, so I can write RA into 4. Okay, RA into 4 equals to MP plus 150 into 2. Okay, I'm taking the summation MD equals to 0. It means that summation MD is 0, right? This unit load with this load will not contribute any moment because it is acting at this point D. Okay, so if you calculate RA from here, so MP here is 135. Okay, so 135 plus 135 plus 150 into 2 divided by 4. So RA comes out to be 142.5 kilonewton. Okay, and RB will be 150 plus 60 minus 142.5, right? So RB is 67.5 kilonewton. Okay, so RB value is 67.5 and here RA is 142.5. Okay, now we'll draw the bending moment diagram. Now if you draw the bending moment diagram for the case 2, RA is what? RA is 142.5. Okay, so and here the MP is acting, which is 135. So our bending moment diagram will fall below this axis. Okay, so this value is 135 kilonewton. Okay, at this C point, let us calculate what will be our moment value. So at C, MC will be equals to 142.5 into 2 minus of 135, right? So this value will be 142.5 into 2 minus of 150. So you can see that, and this is basically positive. So you can see that here the moment is coming 150. Okay, and here this moment will be 135. Okay, now you can see that this bending moment diagram, we can see that it is not satisfying the yield condition. It is not satisfying the yield condition. Okay, yield condition is not satisfied. Yield condition is not satisfied. Why it is not satisfied? Because you can see that moment at this C point is 150. Okay, and MP value is MP value is 135. So M is greater than MP, which is not possible. Okay. So what true mechanism is what? True mechanism will be when the plastic hinges are formed at A and C. So you can say that the design plastic moment capacity for this problem, for this cantilever beam is, so required plastic moment capacity will be 144 kilonewton meter. Okay, so this is the very, very good problem, right? So we have discussed about what is the importance of checking the yield condition. Okay, from that we get the idea which moment is our design moment, which moment will be our design moment, right? So 144 kilonewton will be our design or required plastic moment capacity for this collapse load system. Okay, so the cross section you should design the cross section which will give the plastic moment capacity of 144 kilonewton meter, because the plastic moment capacity is as a function of cross section, area of cross section. Okay, right? So area of cross section and material, which type of material it is, right? So now you can see that now if someone asks you the questions, okay, so you always choose which your design capacity should always be your highest plastic moment which you are getting. Okay, you will be on the safe side, right? So if some objective problem is there, if you find from the first part you get the plastic moment capacity of 144, from the second part you get the plastic moment capacity of 135, let us suppose. So in the objective question you don't need to check this one, whether it is satisfying the yield condition or not. You directly mark which is the highest moment capacity, right? Why this thing is why we choose it highest, we discussed over here. Okay, guys. So as you can see that biologically also you can say that for this collapse system to occur, you can say that if this load system will have to be collapsed, then the moment capacity should be maximum. Okay, required plastic moment capacity should be maximum. Okay, guys. So if you have any doubt regarding this problem, you can write in the comment section. Okay, like why we need to check this yield condition, those things. Okay, try to carefully see this problem. Okay, this is a very good problem. So we'll meet in the next lecture.